Hello everybody, I'm Shahram. I'm a PhD student at York University. And today I'm going to talk about Naïve based algorithm, which is one of the most important algorithm for text classification. Now, when most people want to learn about Naïve Bayes, they want to learn about the multinomial Naïve Bayes classifier, and that's what we talk about in this video. However, just know that there's another commonly used version of Naïve Bayes called Gaussian Naïve Bayes classification, which will be not covered in this lecture. In this lecture, first we will see how we can use Naïve Bayes algorithm to classify normal emails from spams as a simple example. Then I'll describe the intuition of Bayes algorithm and also concept of backup words to solve the relatively more complicated problems. Then we will formalize the naive Bayes classifier. Finally, we will learn how we can learn parameters for naive Bayes algorithm. Imagine we receive normal messages from friends and family. And we also received spam, unwanted messages that are usually scams or unsolicited advertisements. And we wanted to filter out the spam messages. So the first thing we do is make a histogram of all the words that occur in the normal messages from friends and family. We can use the histogram to calculate the probabilities of seeing each word, given that it was in a normal message. For example, the probability we see the word dear, given that we saw it in a normal message, is 8, the total number of times the word dear occur in normal messages, divided by 17, the total number of words in all of the normal messages. And that gives us 0.47. Likewise, the probability that we see the word friend, given that we saw it in a normal message, is 5. The total number of times friend occurred in normal messages, divided by 17, the total number of words in all of the normal messages. And that gives us 0.29. So let's put that over the word friend so we don't forget it. Likewise, the probability that we see the word lunch, given that it is in a normal message, is 0.18. And the probability that we see the word money, given that it is a normal message, is 0.06. Now we make a histogram of all the words that occur in the spam. And we calculate the probability of seeing the word dear, given that we saw it in the spam. And that is 2, the number of times we saw dear in the spam, divided by 7, the total number of words in the spam. And that gives us 0.29. Likewise, we calculate the probability of seeing the remaining words, given that they were in the spam. We calculate for the lunch and money. Now, because these histograms are taking up a lot of space, let's get rid of them, but keep the probabilities. Here is there's a terminology because we have calculated the probabilities of a discrete individual words and not the probability of something continuous like weight or height. These probabilities are also called likelihoods. Now imagine we got a new message that say the dear friend, and we want to decide if it is a normal message or spam. We start with an initial guess about the probability that any message, regardless of what it says, is a normal message. The guess can be any probability that we want, but a common guess is estimated from the training data. For example, since 8 of the 12 messages are normal messages, our initial guess will be 0.67. Here we see how we got it. We can see here that there is another terminology. The initial guess that we observe a normal message is called the prior probability. Now we multiply that initial guess by the probability that the word dear occurs in a normal message, and the probability that the word friends occur in a normal message, and also here we just plug in the values that we worked out earlier and do the math for the dear and friend. Now we just plug in the values and we get 0.09. We can think of 0.09 as the score that dear friend gets if it is a normal message. However, technically, it is a proportional to the probability that the message is normal, given that it says dear friend. So we need to consider that probability as well. Probability of normal message given dear friend. So let's put that on the top of the normal message so we don't forget it. Now, just like we did before, we start with an initial guess about the probability that any message, regardless of what it says, is spam. And just like before, the guess can be any probability that we want, but a common guess is estimated from the training data. And since 4 of the 12 messages are spam, our initial guess will be 0.33. So let's put that under the spam so we don't forget it. Now we multiply that initial guess by the probability that the word here occurs in spam, and the probability that the word friend occurs in spam. And also we plug in the values that we worked out earlier and do the math, and we get 0.01. Like before, we can think of 0.01 as the score that dear friend gets if it is spam. Again, technically, it is proportional to the probability that the message is spam, given that it says dear friend. And because the score we got for normal message, 0.09, is greater than the score we got for spam, 0.01, we will decide that dear friend is a normal message. So Naïve Bayes is a simple classification method based on a Bayes rule, which in the previous example we saw how it works, and we will explain more in the future slides. Naïve Bayes relies on a very simple representation of the document called the backup words. Let's look at the backup words concept. Here's a sample movie review. I love this movie. It's sweet, but with satirical humor and so on. In the backup words representation, we imagine all the words from this review thrown into a big paper bag and mixed up together. So we don't know what order the words occur in. So there is the word I, and there's the I in the bag, and the word love is here, and there is a love in the bag. Love is here and love is in the bag, and there is this in the content, and we can see these in this back of word. So actually, we don't know what order the words occur in. So there is the word I, there's word love, and there is other words in the back. But you see that the back doesn't represent the ordering of the words. And we can think of this back of words as really just being a list of words and the counts, like this. The word, it occurs 6 times in this back. Here's 1. Uh, we can see the other counts for the other words as a list of words here. The job of the classification function, we can think of it as a function gamma that takes this list of words and counts and makes a classification decision a thumbs up or thumbs down. If we are doing a classification, or if we have more classes, we can map it to one or more classes. So our job is to map from this list of words and counts to some class in classification. Excuse me. In classification, we have a document D and a class C. And our goal is to compute the probability for each class of its conditional probability given a document. We're going to use this probability to pick the best class. And now, how do we compute the probability of a class given a document? By Bayes' rule. Is equal to the probability of a document given the class times the probability of the class over the probability of the document. And let's see how to use that in the classifier. The base class, the maximum posterior class, the class that we are looking for to assign this document to, is out of all classes, the one that maximizes the probability of that class given the document. So we are looking for the class whose probability given the document is greatest. By Bayes' rule, that's the same whichever classes maximizes probability of C given D also maximizes this equation. The probability of D given C, probability of class multiplies the probability of class over the probability of the document. And as it is a traditional in Bayesian classification, whichever classes that maximizes this equation also maximizes this equation and this equation. And what we are done here is we are dropping the denominator, crossed out the denominator. Why is it okay to cross out this denominator? To cross out the denominator, probability of D is how likely the document is. Now, if I give you a document and I say which of these 10 classes does this class belong to, and if for each of these classes I am computing the probability of the document, giving the class the probability of the class and the probability of the document, the probability of the document is identical for all 10 classes. For each classes, one more time, I have to compute the probability of the document. And that means that if I'm computing 10 things, each of which is divided by probability at the document, the probability of the document is a constant. And I can eliminate that. So the most likely class, C map, is that class which maximizes the product of these two probabilities. The probability of the document given the class, we will call that the likelihood, and the probability of the class, we will call that the prior probability of the class. So the most likely class is the one that maximizes the product of these two probabilities. The probability that the class will turn out to be relatively simple to compute. What do I mean by the probability of a document given the class? What do I mean to say this particular movie was, how likely is it given the class positive? It seems like a very complicated and confusing thing to compute. And one way to operationalize that is to say, let's represent the document by a whole set of features and x1 through xn. So when I say the probability of a document given a class, all that means is the probability of a vector of features given the class P of D given C. And we are going to represent that probability by the joint probability of x1, x2 through of xn given the class. In other words, we're representing this document D as a set of features x1 through xn. That is still doesn't tell me how to compute this probability, but that is a start. So let's talk about these two pieces now. How do I compute the probability of a class? Well, really, that's just asking how often does this class occur? Are positive reviews much more common than negative reviews? Computing the probability of a class can be done just by counting relative frequencies in some corpus or dataset. So the probability of a class is relatively easy to compute. What about the likelihood of the document of these features in a document given the class? Well, there's a lot of parameters for this probability. If there is n different features and each of them has a certain length, that's a lot of parameters that have to be computed. And we have to compute them one for each class. So that's far too many parameters that we could possibly compute. We can only estimate this number if we had a huge number of training examples, and we usually don't have such an enormous amount of training example. So we are going to make some simplifying assumptions in the naive based classifier to make this computation more possible. The first simplifying assumption we are going to make is called the back-of-boards assumption. And we are going to assume that the position in the document doesn't matter. So this is what I gave you the intuition of a few slides ago. The position of the words in the document, whether it is the first word or the seventh word or 115 words, isn't going to matter. All we care about is which word or which feature occurs. And the second assumption we are going to make is we are going to assume that the different features, x1, x2, x3, their probabilities are independent given the class. So whether one feature occurs given the class or whether another feature occurs given a class are independently going to be true. And of course, both of these assumptions are incorrect simplifying assumptions. They are absolutely wrong. They are completely not true. Nonetheless, by making these these incorrect simplifying assumptions, we can make our problems so much simpler than in practice. We are able to solve the problem with a high degree of accuracy, despite the simplifications. So the result of these two simplifying assumptions is we are going to represent the probability, the joint probability of a whole set of feature x1 through and conditioned on a class C as the product of a whole bunch of independent probabilities, probability of x1 given the class probability of x2 given the class probability of x3 given the class and so on, up to probability of x n and given the class, we are just going to multiply them all together. We are not going to care about x1 which position that occurred in. All we care about is that it was this particular word or feature, and we are not going to care about the independencies between x1 and x2. In other words, in order to compute or simplifying a naive Bayes assumption to uh, compute the most likely class by multiplying a likelihood, the probability of a whole join string of features times a prior probability of a class. We are going to simplify that and say that the best class by the naive Bayes assumption is that class that maximizes these the prior probability of the class. So that's the same. But now, more simply, we are gonna multiply for every feature in the set of features the probability of that feature given the class. Much more simpler equation. So now looking specifically at text. First, we are gonna look at all position, all word position in a text document. So we have a text document and it has 100 words in it. So for all position of words, number one position, number two, number three, we are going to take a look at all the classes. And for each classes, we are going to say what's the probability of the class. And then for each class, we are gonna walk through every position in the text, sorry. And for each position, we are going to look at the word in that position and ask what's its probability given the class I'm looking at. Now that we understand the basis of the naive Bayes classification, excuse me, let's look at a slightly more complicated example. This time, let's try to classify this message: lunch, money, 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 money. Note, this message contains the word money 4 times. And since the probability of seeing the word money is much higher in spam 0.56 than in a normal message, then it seems reasonable to predict that this message will end up being spam. So let's do the math. Calculating the score for a normal message works like just before. We start with the guess, P probability of N, normal message, and the probability we see money 4 times, given that it is in a normal message. When we do the math, we get this tiny number. However, when we do the same calculation for spam, in other words, if a message contains the word lunch, it will not be classified as spam, as we get 0 for that calculation. And that means we will always classify the message with lunch in them as normal, no matter how many times we see the word money. And that's a problem. To make run this problem, people usually add one count represented by a black box to each word in the histogram. To work around this problem, people usually add one can't also for the other classes like spam here. The number of cons we add to each word is typically referred to the with the Greek letter say alpha. Anyway, and now we when we calculate the probabilities of observing each word, we never get zero. For example, the probability of seeing lunch, given that it is in spam, is 1 divided by 7, the total number of words in the spam plus 4, the extra cons that we added, and that gives us 0.09. Note that adding cons or black boxes to each word doesn't change our initial guess that a message is normal. And for or message is spam, doesn't matter. Now when we calculate the scores for this message, we still get a small number for the normal message. But now when we calculate the value for spam, we get a value bigger than 0 that you can see here, a tiny number, but it is not a 0. And since the value for spam is greater than the 1 for a normal message, we classify the message as a spam. So in this lecture, we saw how naive Bayes algorithm works. We try to formalize the naive Bayes classifier and also how naive Bayes learning parameters or algorithm works. Here is the references of this lecture. We use the example explained at this website, and we also try to formalize the example by getting information by in the books written by Jarabsky. And thank you for your attention. If you have any question, feel free to drop me email.